Now let's turn our attention to an ellipse. So an ellipse is the set of all points for which the sum of their distances from two fixed points, known as the foci, is constant. So we have two focal points here. So for instance, this point right here, F, and this point right here labeled F prime, these are the two focal points for the ellipse. And then what we're saying is every single point on the ellipse, so here's 2 points, we got A and then Q later on. We're saying that the distance from the focal point to A, well actually both focal points to A, so I'll call this D1 and D2, that remains constant. So D1 plus D2 equals some constant value C. And that would be true even at a different point. So the distance, I'll call this just D2 again, even though clearly it's not the same length, but the idea is that the sum of these two lengths would always be the same value. And that's how an ellipse is formally defined. Now, some important parts of an ellipse. We have, first off, what's known as the major axis of the ellipse. And the major axis is just, it can either be horizontal or vertical. You can sort of picture an ellipse like a squished circle, and whichever side of that ellipse is longer, that defines the direction of the major axis. So it could be vertical or horizontal. And then we have the minor axis going the other direction. And of course, this ellipse doesn't necessarily have to always be going through the origin. You can have any kind of center point with coordinates h and k. And then the minor and major axis can be shifted as well based off of that. Now, one thing that is useful, we have two vertices in an ellipse. So labeled point P and P prime here. These are the vertices. So P and P prime are vertices. Now, it's tempting to call Q and Q prime vertices as well, but by definition, they're really not vertices. I've even seen textbooks violate that and call them vertices, but you only have vertices along the major axis. And one thing that is important about that is the distance from the center of the ellipse to the vertex on the major axis is called a distance A. And the distance from the center to the other point along the minor axis is called a distance B. And in an ellipse, it is always true that A is greater than B. Right? So that's something that we use in developing a formula for an ellipse. That's a really important concept. And then if you'll notice, we have F, and I know there's a lot of things happening on this graph, but bear with me. We have F labeled with a point C away, right? And it is no mistake here. These A, B, and C do not form a right triangle, but it's sort of related. Anyway, the relationship between these is that C squared is equal to A squared minus B squared. That's another really important principle that you need for working with ellipse equations a lot of times. All right, and I'll show you the basic equation of an ellipse, but I first want to show you how these distances really are this constant all the way around for all points on an ellipse. So let me bring up an app to help you there. Okay, I have a setup here, and in this setup I can define the location of two focal points wherever I want them to be. And then the distance A from a center point, and the center point isn't labeled, but it would be halfway between the focal points. Anyhow, let me clear that part out. If you'll notice, I've got point P over here, and I've measured the distance from P to one of the focal points and P to the other focal point. And the sum of those two is always added up right over here. So right now I've got 9.78 plus 7.45 equals 17.23. Now, as I move P, clearly the distances between the point P and the two focal points changes, but it stays at a constant total of 17.23 units. All right, and the point A that I've labeled over here, that is the distance to a vertex. So I'll go right through that point, and that will draw the ellipse. Now, the closer those focal points are together, the more circular your ellipse would be. So for instance here, I got them very close together, and it's really not that discernible as an ellipse versus a circle. But if I move those focal points far away, I can get something that is very heavily elliptical. So there we have it. Now, defining a formula for an ellipse, here's what we have for standard form. So either one of these two equations right here. And if you'll notice, they actually look fairly similar to the equation of a circle. And in fact, they really are, because you have x minus h quantity squared over some constant plus y minus k quantity squared over another constant equals 1. For a circle, it looked like x minus h quantity squared plus y minus k quantity squared equals a constant squared. And so really, if I multiplied both sides by a squared times b squared, I kind of have it in a form that would look very similar to a circle in that respect. But it doesn't quite ever work out to where these two values would ever both disappear. Because even if you multiplied the entire equation through by a squared, for instance, like you would cancel out this one, but you'd still have an additional a squared over here. So you either have these constants on the, oh, sorry, that would cancel on that one. Either you have the constants multiplying these terms, or you have them dividing, and the general way we treat them is through division. All right, so it looks very similar to a circle, and it has a lot of the same similar properties as a circle. All right, so the center is very easy to find. It's just the coordinates h and k. And then if we use the values a and b, notice these are squared underneath these terms, so you do need to take the square root of them, similar to what you had to do with the radius of a circle. That gives you the length of the minor axis and the major axis. And technically, A would give you half the length of the major axis, so you just adjust accordingly. Now, if your major axis is vertical, remember A is always larger than B. Sorry, if your major axis is horizontal, then A, the larger of these two values, is under your x-coordinate. If your major axis is vertical, then A, the larger of these two numbers, so sorry, A is greater than B is what I wanted to write, is going to be under the y-coordinate. So whichever number is larger, that tells, and whichever coordinate that's under, either x or y, it tells you if your major axis is horizontal or vertical very easily. And then you can use the relationship I gave you here to determine the location of the two focal points, or foci is the other way we say that. And you can locate them basically just by taking, in this case it's mentioning for the change in the y. So this would be if your major axis was vertical, then you would change the y coordinate on your center, just do plus or minus whatever c ends up being. Of course, if your major axis is horizontal, just add or subtract c to the x coordinate of your center. So let's look at some examples. So first off, I have an equation that's in general form, and I want to put it into standard form and then graph the resulting ellipse. So let's get started here. First off, what I can do is separate all the terms that have x's from all the terms that have y's. So this would be 4y squared plus 24y, and then move the constant to the other side, so that's equal to negative 36. And we're going to add in some things in just a moment, so don't worry about this being negative. It probably won't stay negative the whole time. Now, when completing the square, I do need to factor out any coefficients of the squared values. So I would need to factor out a 9 from the first set of parentheses, so that would be x squared minus 4x. Then I would need to factor out a 4 from the second set, so y squared plus 6y. Now, in completing the square, take the number, the coefficient multiplying x, divide it by 2, so that would be 2, square it, that gives me 4. Now be careful, if I'm adding 4 right here, everything in this set of parentheses is being multiplied by 9. So I'm actually adding 36 to this side of the equation. So to keep everything balanced, I have to add 36 over here to this side. Similarly, when I take 6, divide it by 2, that's 3, 3 squared is 9. Everything in this set of parentheses is being multiplied by 4. So when I add 9 right here, I am in fact adding 36 to this side of the equation. It's the net total that you're adding that you have to account for. Alright, so once that's done, I now have 9 times x minus 2 quantity squared plus 4 times y plus 3 quantity squared, and this adds up to just 36. And lastly, what I need to do is divide everything through by this constant value over here, because in standard form we always have these values, the ellipse set equal to 1. So nicely, 9 goes into 36 4 times exactly. 4 goes into 36 9 times. And 36 over 36 is 1. So now I can go through and identify important pieces of my ellipse. So for instance, the easiest thing is the center. You just read the center from the values inside the squared terms, taking care to make sure you use the negative of those values. So x minus 2 gives me an x coordinate of positive 2, y plus 3 gives me a negative 3. Now, a and b. So a is the square root of the larger of these two numbers. So the larger of those two numbers is 9. The square root of that is 3. The smaller is 4, and the square root of that is 2. So that gives me a and b. Which means I can now calculate c, because c squared is a squared minus b squared, which would be 9 minus 4, or c is going to be the square root of 5. And technically it is the plus or minus square root of 5, but the thing about that is we know that we're going to add and subtract the value c to get our 2 focal points in the ellipse, so it's kind of understood. But if you wanted to be careful, that would be perfectly fine to go ahead and write that in. Okay, so we really have a lot of information here for our illustration. So let's go ahead and start plotting some things on here. So 1, 2, 3, 4, 5. 2. That should be sufficient. All right. Center is at 2, -3. So 2 on the x, -3 on the y. So there's my center. The value of A is 3. And this could either go, like 1, 2, 3 this way, or 1, 2, 3 this way. We have to decide if our major axis is horizontal or vertical. Well, the value 9, that's the larger of these two numbers, is under the y coordinate. So that tells me that my major axis is on the vertical axis. All right, because y is the vertical variable. It's pretty easy to remember. All right, so I would go 1, 2, 3 units up here. That's one of my vertices. 1, 2, 3 units down this way, and that's my other. B is 2, so that means I go 2 units this direction and 2 units this direction. And that gives me enough to draw my ellipse. And if circles are difficult to draw, ellipses are a little bit more so to get them rounded just right. So do your best, that's fine. And then the focal points. So the focal points are always going to be inside the ellipse. Square root of 5 is smaller than 3. Let's just get an approximation here. Square root of 5 is 2.23. So just a little bit beyond 2. I'll do a different color for the focal points. So there's one focal point, and there would be the other, just about 2.23 units away. So got my focal points, the coordinates of those if I need them. So they're along the same vertical axis as the center. So the vertical axis of the center is at 2. And then we just go from the center, starting from -3, and then go up the square root of 5. And the other one, we just go down the square root of 5. Okay? And then that labels those particular points. If we need the labels for the vertices, again, you can memorize formulas for this stuff, but it's not really necessary, especially if you just take a moment to draw a picture. So this point is at 2, 0, and then this coordinate is at 2, and let's see, that's -3, -4, -5, -6. And there we have it.